Good. So now everybody should hear me online as well. Sorry, I didn't notice it was muted. So hopefully everything is fine online now. I will open Discord, so I will try to catch up there. Yeah. So yeah, everybody managed to find this repository? Yeah, just tell me if you cannot find it. But if you Google like ADDD my name GitHub, it should appear as one of the top results. Yeah, so in this repo, there's actually both of the tutorials for today. So how many of you are actually coming to the de novo drug design tutorial as well? So, some of you. Okay. Yeah, so we will be working with the same thing. Um, so basically, I made everything work in Google Colab, so you can just control click and it's gonna open Google Colab. So I already said on Discord that you will need a Google account for this to work. So hopefully you have one. If not, yeah, then probably you need to create one. Um, so yeah, so today we will be opening this one, the hem space slash tutorial. And so who's used to Google Colab? Who's used it before? Yeah, not that many people. So I'll try to go slow. Um, and Jupyter Notebooks, who worked before with Jupyter Notebooks? Yeah, all of you basically. So that's great. So I guess you all know all the shortcuts. So yeah, if you don't know, like so escape A, that will add a new cell. And what we need to do first is what yeah to basically run the installation code. So I'll walk you through it. So basically, if you want, you can persist all the files on Google Drive. So uh, you can run this code, but you can also adjust things so that it doesn't save it there. But then you need to maybe edit a little bit this script in the repo. So you can basically use these commands and change them accordingly. But for this tutorial, I sort of assume that you want to persist everything so that you can come back to it. Um, so that's basically the first part where it connects to your Google Drive. Um, then it's going to install some dependencies. And this is just an example of how you can change to a different directory. So we can just copy this, go to the tutorial notebook, and we just paste it in the top cell. Yeah, it's going to ask you if you want to run it or not. So you need to agree to that. Yeah, for this tutorial, we don't really need. Yeah, now it asked me if I want to connect my Google Drive. So yeah, I'm actually not logged in here. So oh, somebody is logged in here. I don't know who that is, but okay. Don't want to don't want to put stuff in somebody's Google Drive. So yeah, in the meantime, you can try to run this, but I will try uh to yeah, but I'm sharing. I need to change the sharing now. Uh, I will share the whole screen. I'll go to anonymous browsing. No. Mm. Yeah. Didn't think anyone would be logged in here. Yeah, so I'm just gonna put the code here, run it, and yeah, just put. Um, okay, so hopefully now it's gonna let me do the thing. Yeah, so yeah, it will ask you to connect to the Google Drive. Okay, asking more questions. And just click continue, continue. Yeah, so th this looks good. So anybody has problems running this? Yeah, yeah. I mean, I can check. We have time, so it's going to be a short one. So it's 1 hour, right? This session, I think. Oh yeah, yeah. So the if you see an error, but then the output continues, it's fine. So there's some error about like NumPy something something. You will see it on the screen. So you don't have to worry about that. Yeah. So yeah. Anyone having problems? Just let me know if you want advice. Yeah. Yeah. So okay, yeah, so you need to go to the repo. Musíš na ten repozitář, jestli ho tam máš. No, je to add chemspace de novo, tak když to nějak vygooglíš, přímo půjdeš do toho repa, tak tam je readme file. Jo. Mhm. A tady je kole, tam už seš. Needs help? No? Yeah, so yeah, maybe you noticed that there is some error. We don't need to worry about that. It should install fine. Um, so yeah, so you will notice that it puts you in this hemspace work directory. Um, so what you can do in Python, you probably know that. So you can always um, check if your working directory is correct. So I just want to show that what we want to be in is this directory. Yeah, still need to hide this. It's annoying. And if you go to Google Drive, uh, hopefully I can go there. Yeah, then you will actually see that this folder appeared here with another folder in it, and that's the whole repo. So whatever we now have here, it's also mirrored to here. So you can see we are in my drive, add main, and all this stuff. So this is a way to persist stuff on Google Drive on your in your Colab environment. And then you can try to run this code. I think maybe it will not run. Yeah, because we have some mismatch. So uh, because of some of the dependencies, you actually need to restart uh, the environment so that you load the packages that you just installed. So yeah, if you get this error, it's new, so I didn't have a chance to fix it. I just discovered it yesterday. So you need to restart this again, restart relation, or I don't know how it's called. And then if you run this code, you will actually realize it put you in a different directory. So that's why I was mentioning it in the beginning, that you need to make sure to be in the correct directory. So to change into another directory, you can just do percent mark cd and then just paste, oh, no, and then just paste the path where you want to go. So in this case, it's this content hem space blah blah. Yeah, and then the code above, it should show you again the correct path, and the code now should work. Yeah. So yeah, basically in this tutorial, it's going to be very easy. We have basically a set of compounds. Some of them are from Campbell, and they traditionally bind proteins, but some of them are RNA binders. So this is from a project that my student did for his diploma thesis. And basically it consists of two sets of like distinct chemical spaces. So what we're going to explore is basically how to use some chemical space visualization methods to see the patterns and similarities between these two chemical spaces. Yeah. So everybody managed to run the first cell like this here, and they see the data with the RDKit molecules.
Yeah,
Not yet?
there was some other errors.
There, oh, you got other errors. Yeah. So that's what I was saying. For that, you need to restart your session. So I don't know, this is not in English. So yeah, so you need to, after you install all the packages, you need to restart the kernel basically to load the new modules. But yeah. That's a good point. Yeah. Like this, or maybe I can also make it full screen. Yeah, but this keeps coming up. Yeah. So after you restart the session like this, uh, run this code and check what directory you're in. And if you're not in this hem space directory on your Google Drive, then just change directory into it. So don't forget, because that's otherwise it will not find the data. So just make sure you're there. So yeah. Anyone else has issues or questions? Like whenever you have questions, just ask like about whatever. Yeah. So okay. So we basically loaded these RNA binders data set. So yeah, we just delete some stuff here. That's not important. So you can basically go down and just follow the execution of the cells. So now we're gonna load in this variable, we're gonna load the protein binders. So we have now two data frames, one with protein binders, another with RNA binders. Then we want to yeah, do some renaming so that we can visualize things a bit better later. So you can just uh, change this stuff. And here basically uh, we concatenate the two sets after we prepare them. Um, you can see there's some metadata. We have some unique IDs for the molecules, names, miles, inch keys, blah, 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 some descriptors. But we will gonna calculate more. But then an important one is we have this set variable, which distinguishes protein binders from RNA binders. So that's what we will be using for coloring our depictions. And here we're using our QSPR-PRET framework to basically merge this data together into one data set. And we wrote some tools around this data representation that make it a bit easier to just do stuff. So yeah, this will take a while. I don't know why on Google Colab this takes so long. It's like normally it takes just, I don't know, half a second, not that long on if you run it natively. So we just need to wait for it. But yeah, in QSPR-PRET, basically you have different data representations for different things. So molecule table is the most basic one, where you can basically wrap a data frame in it, and it saves some metadata about your molecules, does some standardizations and checks as well. Um, yeah, yeah. Maybe if you want, after this is finished, maybe we can run the whole notebook actually, so that we don't have to wait. So what you can do is go to run, and then you can, uh, yeah, just so yeah, sorry, it's in check, but you can run this cell and everything below. So yeah, so then it's going to evaluate the whole notebook, so you don't have to wait for things to execute. Yeah, so like for chemical space visualization, you can do a lot of different things. Uh, the some of the visualizations are really basic. What I really like is just showing molecules that I'm interested in a grid like this. You can enhance it with some smart search. So uh, yeah, in this in this cell, I'm just using the QSPR-PRET function to like search in the data set with smarts. And then I'm using this package that's called most to grid, which basically gives you this nice interactive HTML page uh, that also has integrated smart search. So if it's maybe certain scaffolds that you're interested in, so in this case, this is sort of an RNA specific binding pattern from this publication, then it makes it easy to basically highlight the molecules you're interested in and explore basically what's in your data, like how many compounds have this pattern. So I would say that's probably a lot of you know about this stuff, but I think this most to grid package is a really nice implementation and does all the basic stuff that you would want. So that's why I wanted to show it here. Um, then on the next one, we're just going to calculate some RDKit descriptors. So Wim was talking about them. You can use them for QSAR, but you can use them also as an input to some dimensionality reduction methods that we will talk about later. Um, so here it's basic RDKit descriptors. Probably you're familiar. Not going to go into detail about that. Um, and we're going to add some of them as a property to our data set because I think like you don't need really fancy visualization to see some like main differences between data sets. So I would say histograms are also a nice choice, where basically you can look at the different variables that you're interested in. Um, can also be like QSAR model predicted values or whatever. And just using Seaborn, you can get a nice overview of how different variables are distributed between sets. So we can see that the RNA-based set probably is less diverse already, because when we look at QED, like it's much more well behaved, and yeah, also in terms of molecular weight, generally these molecules are also like a bit less diverse. So yeah, in general, I think histograms like nice to visualize differences between sets of molecules. And I think, yeah, we will also use that in the de novo drug design tutorial like this. And then also, I would mention scatter plots are really nice, where you want to see maybe how much molecular weight in this case affects some variable like log p. So already you can see some relationship and especially outliers uh, in these visualizations. So you can see there are some uh, molecules that are maybe a bit unusual, some extremes. So yeah, scatter plots also really good for that. And especially when you want to easily interpret the results, it's really nice. Like you clearly see, like you know what the axis means, which is not true for the other methods that I will show. Um, yeah, you can also enhance this visualization with this density plot. So probably you know how to read a map. So these are basically like if you have a hill, and so you have these like equidistant lines. I don't know how they're called, or like basically the line means that it's in the same height. So here it denotes like the basically the higher the hill, the higher the density of the data. So you can actually see like most of the data is distributed like in this bracket, like molecular weight from 200 to 400, or maybe like 450, and QED like zero point 0.4 to 1. So you can see like most of the density of the data is here, which is really not obvious like when you have a scatter plot like this. So that's, yeah, another thing I wanted to show. Um, now we're going to go to like the, let's say, more fancy visualization methods, um, which rely on dimensionality reduction. So if you remember those descriptors um that we calculated, um, then this is basically taking this 200 something descriptors and is going to try to reduce them into a 2D plane for us to maybe still be able to see some patterns and conserve sort of the differences between the different molecules. And mainly, this is useful to basically see clusters or groups of molecules that are similar. So we will see how that works in this case. So what you need to do at first, because the descriptors, they are on different scales. So you have molecular weight, which is like in terms of hundreds. Then you have log P, which is like up to 10. Um, so you need to scale everything to sort of the same scale. So that's what we do in this cell using scikit-learn. Um, And in this like ginormous big cell, I prepared examples of some of the dimensionality reduction methods. So here's a question for you. If you can guess like what each parameter is doing to when you look at the plots below. So there will definitely be differences between the methods, but also depending on the parameters that you use. So I'm just gonna quickly talk about each method. So PCA, I think everybody knows. Like who knows PCA? Yeah, yeah. So, some of you, okay. So PCA is basically like the most simple method. Um, it basically tries to conserve variance it finds in this like multidimensional space, and then project it like in the best way to the 2D plane by basically converting everything uh, to like what's called principal components, where like the highest like principal components have like most diversity of the data. So if you look at the first two principal components in this like transformation of the data, you should be able to see like the most diversity from the data. And what's good about this method, it's really grounded in linear algebra. So the transformation that you do, if you do not change the input in any way, you always get the same transformation. So if you want to add a new point to your PCA, you just transform that one point, and that gives you the new coordinates in your like 2D transformation. So that's why this is nice. because you can easily add new points, but every time you have the same data, you get sort of the same image, which is not true for the other methods. So one of them is UMAP. Uh, so UMAP, I think I have, maybe I can go here. Oh, it doesn't work anymore. Let's see. Yeah. So they have a really nice web page to explain UMAP. Uh, so this one uh, basically what it tries to do, like really in a simplified way, is to find similar points in the multidimensional space and sort of like squeeze them together while also like repulsing the more dissimilar points. And then that's what basically it shows you in the 2D plane. So you can basically look at like transformations of the different data set. So you have like these different complex um inputs that it then tries to uh, convert. So you can play with it. This is yeah, kind of fun. Um, yeah, they also have like some 3D transformation of data sets like that t-shirt shops and t-shirts are close together. So I highly recommend just checking this out. Like we don't have much time, but it's, I think especially this example is really nice where you have this mammoth and you can play with different parameters and you can see how UMAP basically changes the 3D data into 2D projection. Yeah, so what the representation that you're basically looking for and the way you want to tune these parameters is that basically you want to get as precise of an image of the original 3D 3D representation or like highly dimensional representation so that it's representative. So maybe I would say like this is a good set of parameters for this one because you can clearly see that this is a some kind of a head and maybe you have the legs. You can still see something uh, about the data, some relationships. So that's this is a good setting. Whereas if you were to do it like this, for example, like it's completely random, doesn't tell you anything. So what I was trying to like basically say with this, and now I need to try to go back, is that the UMAP method really highly dependent on these parameters. So like usually when you use it in practice, don't run it just once, run it several times with multiple parameters and look at the result. So um, here, yeah, we try to use the different settings for comparison. So did anyone already take a look at the UMAPs generated? So what can you say about like these parameters? Just anyone. So I think like a lot of them are self-explanatory, right? So what would you say number of neighbors does to a UMAP? Uh, Guesses?
The KNN for the then the filtration, so it's how many neighbors it considers in the graph building.
Yeah, exactly. So if you basically if you select more neighbors, then it's going to create larger clusters, basically. And if you select less, then it's the clusters will be smaller. And then the minimum distance, that's also like for visualization purposes, an important parameter is basically how far apart the display points are allowed to be. So if you want like really small and compact clusters, then you set it to low values like you see here. So if we actually look at the results, if we scroll down, so oh, it doesn't, huh? Also, it doesn't show the What? Does it show up for you?
Yeah, it works.
Yeah, so for you the interactive visualization works. Yeah, because I'm on Firefox, but you're on
I'm
Edge.
on Firefox.
Oh, okay. Interesting. Yeah. Okay, well, I cannot show it on to the people online, I guess, but at least you see it. So that's good. Yeah. So yeah, that's a shame. But yeah, so if you are following along, which probably you should be, even if you're sitting at home, um, then you can go through the UMAP plots and you will basically see uh, the different representations. So based on what you see, like what would you say the best setting is for this data set? Yeah. No takers. Okay. So yeah,
Second.
yeah, exactly. So yeah, I would also say that because here we're just looking at like general differences between sets. So what you actually can see, it's really a shame that I cannot show you here. But what you see in the second UMAP, like there's a lot of in the Campbell dataset, in the protein binders dataset, there's a lot of steroids. So you will see them sort of scattered around at different places in the other projections, which is probably not what you want, because the one problem with UMAP, and we actually talked about it with your colleague here, is that it can put similar points together, but if it decides that two clusters do not belong together, it can really like put them far apart. So basically, if two clusters are globally far apart, it doesn't actually mean that they will really be far apart in the projection or vice versa. So so yeah, that's the danger of using UMAP, and also like t-SNE, which basically is similar method. Um, the danger here is that you will miss some clusters if maybe you set the size too low uh, or something like that. So yeah, just if you have the interactive projection in front of you, try to look for the steroid data set, and you will see that in, for example, this projection, it's very let's say very distinctly separated, which yeah, for like general analysis, we don't really want. Yeah, and for t-SNE again, it's a similar method sort of to UMAP. I included it here because it's a bit more local than UMAP, and it can, if you want to look at like a series, like chemical series, and you set the parameters right, then it's really useful because in my experience, like most of the time, it can separate, especially when you use fingerprints, it can separate nicely compounds that have the same scaffold into separate clusters. So that's one that's really nice to use, and it has similar parameters. So you have this perplexity parameters, which again is like sort of similar to the number of neighbors, but basically how many things you put in one cluster. Um, and yeah, I don't show any other parameters. So this is like perplexity is the main one basically for testing. Yeah. So yeah, I don't know why it doesn't show. Weird. Yeah, so you can just look at these visualizations and play with the parameters. But the take home message here should be that with these methods, like you never really know what they're doing, and it's more intuitive than it is like sort of rule of thumb kind of thing. You just need to know what you're looking for in the data before you use them. Yeah. So yeah, what I'm also doing here is like the exporting this CSV file. So maybe if you want to then explore it later, you can just get it from your Google Drive, and it has all the UMAP coordinates for the different settings exported. Yeah. Okay. So yeah. So what we have done so far, that's basically like dimensionality reduction based on numerical descriptors. But what you can do is also do it on binary fingerprints, which in my experience, it works a bit better for t-SNE. but we will soon see maybe some paradoxical behavior. So here we're just calculating some Morgan fingerprints. You saw explanation of them at Wim's presentation, so you know. And for working with fingerprints, it actually makes more sense to use this Jacquard distance metric because for all of these methods, you need uh, like a distance measure to say how far the points are in the original space. So the Jacquard metric is basically a Tanimoto coefficient. So if you work with binary data, it makes sense to calculate this metric rather than Euclidean distance, for example. So you can use it here with fingerprints, and again, like the same exercise, basically trying different UMaps and different t-SNEs, again using the Jacquard metric. So if you look at these results, do you see anything weird about the t-SNE? It's the second to last depiction. Maybe if I zoom out, will it show? No.
Maybe refresh. I don't know if you lose the kernel.
Yeah, then I think I lose the kernel if I refresh. No. Yeah, so the second to last t-SNE looks a bit weird, right? It's just a crazy circle. But actually, the last one where I didn't use the Jacquard metric, it looks fine. And the clusters like sort of make sense, I would say. I don't know, maybe you disagree, but I would say the last t-SNE maybe shows sort of the different chemical series a bit better. So that's a bit paradoxical because we would assume Tanimoto coefficient should like make more chemical sense, but yeah, here it just didn't work on this data set. So yeah, I don't really know why. So if anybody wants to take a guess, feel free. And yeah, so again, just showing the density plot that I showed before. And again, like using this more plotly interactive library just to show the same thing. So basically, here you can show the density, but then you can use interactive scatter plot to really like see which compounds are where in this density plot, and you can like sort of zoom in and look around. So this is just like another example. Yeah. And that's like basically everything for the tutorial. So yeah, I think this was just 1 hour, right? So we have 15 minutes. If you want me to come over and just talk about stuff, dial something down, let me know. And yeah, like if anybody has any questions, also online, like I'm looking at the Discord. There's no questions there, but if you want to ask, yeah.